Okay, Assalamualaikum and good morning, everyone.
Salam.
Present screen. Salam. Okay, we will go to the last lecture, lecture number 8, regarding multiphysics modeling using fluid structure interaction, FSI. Topic, students will be able to understand the concept of multiphysics modeling. And your simulation has more than one physics. So we have learned about electrical modeling, solid mechanics, fluid dynamics, and all of that evaluate the fluid dynamics and structural mechanics at the same time. So the function of FSI is the fluid. So we have a fluid flow and how the fluid flow affects the structure movement or deformation of the structure. So when the fluid encounters a structure, the stress and strain are exerted on the solid structure. Or we also known as
Sir. Like, sir, like.
forces, which can lead to mechanics. However, in engineering, usually FSI is used to study blood flow. Yeah. Okay, sorry. Sekejap, best sekali. Okay. Okay. Meshing concept or formulation. We call it Lagrangian or solid mechanics. Or program it yourself. But the concept is important, okay? Ya. Boleh dengar tak? Boleh dengar tak?
Welcome back, sir.
Okay. Tekanan sekejap. Okay, boleh nampak slide?
Boleh, boleh.
Okay, patah balik. Okay, masuk-masuk. Jelas je. Okay, kat bawah tak ada, internet tak kuat, kena naik atas. Okay, yang mana tadi? Okay, anggap skip je lah yang tadi. Okay, so FSI in biomedical engineering, usually we used to study blood flow in our body. Okay, for example, like blood flow through heart valve, and also blood flow through some damaged blood vessel, for example, aneurysm. Okay, so here we sometimes FSI is used in aneurysm because we want to study how the blood flow can affect the rupture of the blood vessel. Okay, so there are two meshing concept or formulation in FSI. So first we have Lagrangian. So Lagrangian formulation is used for solid mechanics, and Eulerian is used for fluid. And these two formulation basically is I think I have explained last week about relativity. Okay, like how you look at the problem either from a fixed point or from a moving point. So Lagrangian I think is on a fixed point, on a moving point, while Eulerian is on a fixed point. But in FSI we have both solid and fluid. So how we can, I mean, which one of the formulation we want to use in FSI? Because we have Lagrangian only for solid and Eulerian only for fluid. So in FSI, we need to create one formulation or new formulation so that it can be used for FSI application. So these two formulation, the mathematics are different, so we cannot use it at the same time. Okay. So in FSI, we call it, we use a mesh reasoning method, or we call it ALE method. Basically, ALE is known as arbitrary Lagrangian Eulerian. I don't know how it basically does in finite element software, but the theory is that what it did basically, it uses something we call remeshing, or after the problem calculated for solid, then to calculate for the fluid, then it will do remeshing on the fluid and apply Eulerian concept on the fluid. So Lagrangian on solid, and then recalculate, apply on the fluid. So all of these ALE, Lagrangian, and Eulerian are already built in finite element software. However, we need to know the concept. Okay, sometimes the concept is important if we want to understand or to analyze the solution later. Okay, ni sebenarnya ada bergerak, so kena play jap. So this is how FSI in a blood vessel through a valve. Okay, so if you look at the garisan here in the middle, represent the fluid flow. So bila ada fluid flow, dia akan buka valve tu. depending on the pressure of the fluid. Okay, so kalau dekat bawah ni pressure dia besar, then dia akan open, then dia akan close balik bila pressure dekat atas ni lagi besar daripada yang bawah. So here we have the fluid part in the middle here, and the blue part here, or the valve here, is the solid or the structure. So the interface between fluid and structure, we call it Fsi interface. So ada dua physics kat sini. Yang tengah ni fluid. So fluid ni dia guna mesh Eulerian. And the solid, the blue one, we use Lagrangian mesh. So the boundary between solid and fluid, we call it Fsi interface. Okay, so usually in finite element software, if you want to use Fsi, dia akan automatically set the Fsi interface. So kita kena just bagi tahu dekat mana fluid dan dekat mana solid. Okay, so kita boleh pergi tutorial. Okay, so in this tutorial, we are going to look at how we can use Fsi to study left ventricle diastole. So diastole is basically the period of the heart or the cardiac cycle when the heart expand. Okay, so kalau tengok jantung ni bila dia mengembang tu, tu diastole. So diastole mengembang, the contract is systole. Okay, when the heart contract, then the process we call it systole. So cardiac cycle is the performance of our heart from the ending of one heartbeat to the beginning of the next heartbeat. So in cardiac cycle, we have two process, okay, two period. First, when the heart muscle relax and refill with blood. So we call it diastole. And contraction and pumping of blood, we call it systole. So during left ventricle diastole, the aortic valve is closed. Okay, aortic valve yang ni, dia akan tutup. And the mitral valve is open. So mitral valve is here. Ini. So when mitral valve open, so blood will flow in from atrium, from auricle, and then when systole, mitral valve akan tutup, so normal blood can flow in, and aortic valve will open to allow blood to flow out through our body. So blood will flow slowly until the left ventricle is completely filled. So when the pressure in LV or left ventricle equals the pressure in aorta, then diastole tamat lah. Okay, kita akan start dengan systole. Okay, so simulation ni hanya untuk proses diastole saja. Okay, so blood flow interaction with LV wall during diastole can be simulated using Fsi. However, to study Fsi usually will require a lot of RAM. Okay, computationally high cost. Kena banyak RAM, processing cost, kena graphic yang best. So in this example, kita akan guna model yang simple je. Okay, so we use 2D axisymmetric simulation for the sake of example, okay, for Fsi. Okay, so kita boleh try tutorial. Lamanya nak buka. Okay, so tutorial FSI. Okay, we start with model wizard. We choose 2D axis symmetry. Okay, so we need to find fluid structure interaction. So fluid structure interaction, either you can type on search here, or you can find it under fluid flow, fluid structure interaction, and then choose the first one, fluid structure interaction. So we have a lot of, I would call it a solver for fluid structure interaction, like fixed geometry, fluid shell, and fluid membrane. So fixed geometry means that the solid structure, the movement of solid structure is not much. Okay, only small deformation only. So we seldomly use fluid solid interaction for fixed geometry. Usually we use fluid solid interaction, the first one here. So double click. Lamanya. Okay, so lepas double click, kita akan nampak ada dua physics kat sini, laminar flow and solid mechanics. And here akan ada automatically multiphysics here. Dan bila drop down akan keluar fluid structure interaction. And another one here in definition, we have deforming domain. So dekat fluid sekarang ni dia akan deform. So sebelum ni kalau buat fluid simulation only, last week punya lecture, kita assume fluid tu tak deform, maksudnya fluid tu fix. Tapi dalam FSI, the fluid is no longer fixed. Dia akan bergerak sekali dengan deformation of the solid. So when the fluid moving or deform together with the solid, then we need to add deforming domain. Tapi dia automatic akan add lah. So the deforming domain here is basically the ALE mesh that I've explained tak berapa faham tadi. Okay. Okay, so we choose, we go to study and choose time dependent. Double click. Okay, so we start with defining parameters. Okay, so ada banyak parameter kat sini. So parameter RV, HTA, TB are basically parameters to draw the heart. Okay. Okay, so now we define the parameter for fluid, the viscosity, mu, and the density. Okay, then we define the parameter for the solid. Rho S here is the density of solid. Kappa is bulk modulus. And here we use two parameter Monet-Rivlin, okay? Monet-Rivlin model. So this is the first parameter and this is the second parameter. Okay. Okay, next we define another global definition because here we want to use the fluid velocity or pressure in the inlet. We want to use interpolation table. Okay, so we define an interpolation function in the global definition. So from here, global definition, just right click and choose function and choose interpolation. Okay, so just fill in the table accordingly. Okay, so we have interpolation table here. So next, interpolation and extrapolation, we change to piecewise cubic. So piecewise cubic. Okay, so try click plot. So kita akan dapat graph ni. Okay, so graph ni is we will use this as the inlet velocity. Okay, this curve is the blood flow velocity in the inlet or at the mitral valve. Okay, now we go to drawing the geometry. So firstly, right click geometry and choose ellipse. So in the A semi-axis, RV plus TA, B H plus TB. And then choose another ellipse or duplicate, yeah, duplicate. RV and H. And then choose rectangle. Position 0.5. And then another rectangle. Okay. And then right click again, choose difference. So object to add is the ellipse. And object to subtract is the rectangle. So now we get our left ventricle with fluid. Okay. So basically, this line here, yang tebal kat luar ni, is the wall of the heart or the left ventricle. And the inside here is the fluid, okay, the fluid inside the left ventricle. Okay, so we continue, draw a line segment, specify coordinates, start ending endpoint coordinates at R0.0, 1392. Okay, so this is our left ventricle. So basically, this section here is the wall of our left ventricle, and this section here is the fluid or the blood in the left ventricle, and the length here from this point from this point to this point, sepanjang-panjang ni is our inlet or our mitral valve, and from here to here is wall, okay, dinding. Okay, so next page. Okay, so now we need to set the physics, okay? So we have defined the parameter and draw the geometry, then we can set the physics. Okay, first we go to the laminar flow here. So we choose the fluid domain only. So by default, it will give both of the domain as the domain to be studied in laminar flow. So as I said, the middle here, the green section here is the fluid, okay, the blood. So we want this section only as the laminar flow. So we can clear the selection and go to the fluid part here and just click, okay. So now the laminar flow is only on the fluid part here. Okay, then we can set the fluid properties. So the density we already defined on the parameter global definition. So we just put rho here. And then the viscosity, mu, okay. And then right click laminar flow, we want to define the inlet. So inlet, we choose this line here. Okay, this is our mitral valve, which acts as the inlet. So we change the boundary condition to velocity. So already here, velocity. And we define the normal inflow velocity. So here we have the table, interpolation table just now. So we just include the velocity according to this table. So to define the velocity, you just put in 1 time divided by 0.5 second. So int1 here, so int1 here is the function interpolation that we created just now. So the function name is int1. So to use this function, you just write int1 and bracket, okay, fill in the bracket with the variable that you want to varies, okay. So here we use time. So the function is the function of time, okay. So we just include time here. So divided by 0.5 second is basically to normalize, okay, normalize the time. So our simulation is for time from 0 until 0.5 second. So we divide by 0.5 because of the time range, okay. Okay, so we already set the fluid part. Okay, yang lain ni by default, okay. And now we go to set the solid mechanics. Okay, so same thing in solid mechanics, the domain automatically they akan define on both of the domain, but we want only the solid part to be defined on the solid mechanics. So you just clear selection and choose the solid part, okay. And then right click solid mechanics, we want to define the hyperelastic material model. So go to material model, hyperelastic, and again choose the solid part. And material model, we want to use 2-parameter Monet-Rivlin. Okay, change the C10 with the variable that we have defined. And the bulk modulus is kappa, okay? And the density is rho s. Okay, and then right click solid mechanics. Prescribe displacement. So we want to fix the top section here so that the top section of the solid will not move, okay? Only the inner wall will move, okay? Inner wall and the outer wall, but the top section here is fixed. So we call the top section here the base, okay? The base of the ventricle. So we choose this section and fix in the Z direction. Maksudnya dia tak boleh gerak naik ke atas ataupun turun ke bawah. Tapi dia boleh gerak ke kiri dan ke kanan, okay? So it can move to the left or to the right, but not upward and downward. So we fix the line there in Z direction, okay? And then lastly, right click solid mechanics and choose fix constraint point, okay? So point, fix constraint. So choose this point here, the top left. So kita nak fixkan point ni supaya tak bergerak, okay? So what happen is that when the ventricle expand later, point ni tak bergerak, tetapi garisan ni boleh memanjang, okay? Boleh memanjang ke kiri dan ke kanan. Tetapi garisan ni tak boleh gerak ke atas ataupun ke bawah. Okay, so after we fix, we set the fluid and solid mechanics, we can now set the multiphysics. Okay, if you go to multiphysics and fluid structure interaction, so by default dia akan detect this garisan biru here as the fluid structure interface. Okay, sebab kita dah set dalam ni sebagai fluid, luar ni sebagai solid, so dia akan automatic cari mana interface antara fluid dengan solid tu. Okay, so dia dah jumpa interface dia kat sini, garisan biru ni. So we don't need to set anything, okay? Dia dah automatically set. Okay, so now we need to set the deforming domain, okay? So we go back to component 1, definition, drop down and choose this moving mesh. And then drop down and choose deforming domain. Okay, so by default dia akan empty. So deforming domain ialah kawasan fluid yang kita boleh assume dia akan deform. Okay, so basically all domain of the fluid can deform. So we just choose all section of fluid. Okay, so we have mesh smoothing type here. So by default dia akan letak yo. So we can choose hyperelastic, Winslow, Laplace. So yang ni semua tak adalah penting sangat, okay? Kalau simulation fail kita boleh tukar lah. Okay, so we need to set the fixed boundary. So right click moving mesh, go to fixed boundary. So dekat fluid juga ada boundary yang akan fix, yang tak boleh bergerak. So we choose the top line here as the fixed boundary. Maksudnya bila ada fluid masuk, fluid ni tak boleh mengembang ke atas lah, okay? Dia hanya mengembang ke arah solid, okay? Ke arah dinding ni saja. Dia tak akan mengembang ke atas, okay? So maksudnya maybe fluid tu tak tumpah keluar, okay? So we fix the top boundary here. Okay, so we have set the moving mesh. Now we can go to study 1. And change the time step. Okay, after that, we can go to study 1 again. Right click study 1. Go to show default solver. Okay, so sebab FSI ni lama, so kita akan tukar sikit setting solver to make it slightly faster, okay? So here, by default, dia akan guna segregated. So we don't want to use segregated, we want to use this direct here. So what we are going to do is we go to direct and choose enable. Sama je kan? Oh bukan ni, silap. We go to time dependent solver, right click and choose fully coupled here, okay? Kita nak solve dia fully coupled means we solve the simulation simultaneously. So segregated here, the COMSOL software will solve the simulation by part, okay? Dia akan solve fluid dulu, lepas tu dia akan solve solid, and then they combine solution, and then they adjust, okay? So meaning that it will solve part by part or segregated. While fully coupled, it will solve both part at the same time, simultaneously. So we go to fully coupled, and in the linear solver here, change to direct, okay? Okay, and then ni semua default, tak payah tukar. So we can try compute, save dulu lah. Okay, we compute. Okay, maybe lambat sikit. Fail.
Ya, itu yang kena.
So maximum number of Newton iteration. Which okay, kelas tamat. So we change this non-linear method to automatic highly non-linear, and then try save, and then compute lagi sekali. Macam mana boleh fail? Fail lagi, damn. Okay. Apa yang salah? Okay, tanda-tanda nak fail. Cepatlah fail. Okay, simulation ni fail sebenarnya. Dia lambat gila. Okay, kita check balik apa yang salah. Hai, buat pasal pula. Okay, kita try lagi sekali. Okay, fail. Okay. Bagus. Tak apa, kita tunggu jap. Ni makan dulu. Lama gila. Okay, saya rasa dia akan solve tapi lambat. Okay, so kita ada assignment sebenarnya. Kalau simulation ni fail, assignment ni nanti saya cancel kan. Tapi saya rasa tak fail. Okay, so apa-apa pun saya brief assignment dia lah. Okay, so assignment 7, final assignment. So basically for final assignment, what you need to do is to follow the step given and try to analyze the simulation, okay? Try to analyze the results. So the first question is plot the 3D revolution. So with 270 degree at time 0.5 second for fluid velocity magnitude and solid displacement magnitude using spatial frame. Okay, bila plot ni korang akan dapat result yang sama macam yang gambar yang terakhir ni. Okay, so question number 2, calculate the volume changes in the LV during diastole. So using the formula here. So here, same with assignment 5, solid mechanics, you need to use integration coupling. So here, you need to use integration coupling, but on the solid domain, okay? So you need to use surface, okay, or domain coupling, okay, instead of boundary coupling. Okay, and then when you calculate, you can get the volume against time. And lastly, plot the average velocity of the blood flow at the inlet against time. So in this one, you need to use average. Dekat results ni ada derived value, average, okay? And then choose the inlet boundary. And you will get graph yang sama macam yang kita plot tadi. Okay, so hopefully simulation ni fail. Kalau fail, assignment ni cancel lah. Okay. Okay, so so that's it for today's class. So for you can start doing your project, and also you can watch, I think, last week video on tips regarding test number 2. So we will do test number 2 on week 13. So now is week 10. So week 11, week 12, week 11, week 12, week 13. So your test will be on 15 January. Okay, 15 January, Friday. And your presentation maybe Thursday ke, the following week, study week, okay? Thursday or Friday. Okay, so that's it for today's class. Any question, you just let me know through WhatsApp, okay? So, Assalamualaikum and goodbye.
Thank you, sir.
Thank you.
Result tu fail ke tak, sir?
Setakat ni dia run okay lagi, cuma dia slow gila.
Okay.
Fail tu, sir.
Dia slow sebab dia guna time step yang sangat halus lah. Kalau dia guna time step besar, dia laju sikit. So saya rasa setengah jam juga kot. Okay, so nantilah saya update kalau fail. Kalau tak fail tu maksudnya kalau saya tak update tu maksudnya tak fail lah. Okay, bye-bye. Assalamualaikum.
Okay, sir.
Goodbye.
Bye. Thank you.
Thank you, sir.
Bye.
Thank you, sir.